Bene. Okay, good afternoon to everybody, and welcome to the February session of the Young Seminar of the Italian Society of Statistical Physics. And this afternoon there are, as usual, two speakers, Chiara Franceschini and Antonio Suma, and the first speaker will be Chiara Franceschini, and Chiara got a PhD in mathematics in the University of Ferrara in 2018, working with Professor Christian Giardina. Then she went to Portugal for a postdoc at the Istituto Superior Tecnico, and working there on hydrodynamic limits and equilibrium fluctuations. She also moved for another shorter postdoc at Berkeley, and since the beginning of last year she is at the University of Modena and Reggio Emilia with a position as RTDA, as a researcher, and today she is going to speak about generalized hydrodynamics for a system of inhomogeneous hard rods. Please, Chiara.
Thank you, Paolo, for the introduction and for the invitation. So indeed, the plan for the next half an hour would be to introduce what is the definition of a hard rod, the system of a rod, and then to show you the macroscopic PDE which the model satisfies, which is exactly the so-called hydrodynamic PDE. And indeed, this work was done during my short postdoc in Berkeley, together with Pablo Ferrari, Dante Grevino, and Herbert Spohn. And I realized that when I sent the abstract several months ago, it was still in progress, but now should be more or less. I mean, it's already available on the archive. Okay, so want to start very gentle. So with the definition of a hard rods, you should think of a hard rods as an elongated particle. It is mathematically defined as a three-dimensional point, y, v, r, where y represents the position of the rod, v is the bare speed, and the length is r. During my talk, of course, it was easier to imagine a positive length, but in general, r can be also negative. So r, little r is in the real number as well. We denote by curly y the set of a rod's configuration, such that two rods do not intersect, and this justifies the name hard. And the element of curly y are all those configurations with a finite number of rods. So given the initial conditions, so given some hard rods, the question is, how do they evolve? So they evolve deterministically, following their bare speed. The only things to clarify is what happens when they collide. What does it mean when they collide? So they collide when the initial point of the second rod, so imagine I have two rods, y1, v1, r1, and y2, v2, and r2. So the initial points of the second rod, y2, coincides with the end point of the first rod, y1 plus r1. So they collide at time t, say at time t, and then what happens is that there is a shift in their position, and they continue their motion with the original speed. So you see, so I have a picture here, which is very, it's a simulation of a collision. So it's this is what I've just said. I have the two rods, the pink and the purple one. So they meet, they swap their position, and they continue their motion with their original speed. You see that only, so here, the model we study is inhomogeneous rod, so R1 and R2 are different. If they were the same, so if for a system of homogeneous rod, then this would be elastic collision, because then the shift would be the same for both rods, so they would be reflecting each other. But if in general for homogeneous rod, it's not the case. So this is the model. Everything is deterministic and reasonable, simple. Okay, so you see that, just one remark, you see that, for example, the purple rod has higher velocity than the pink one, so it got a shift of the length, a positive shift of the length of the pink one. Okay. So before going any further, let me just mention an incomplete background for hard rod system. So people were interested in studying system of hard rods between the 60s and the 70s, and they were mainly interested in a system of infinite number of rods. Then the paper that was more useful and interesting for us was the 82 paper of Boldrighini, Dobrushin and Sukhov, where for the first time they prove rigorously the so-called hydrodynamic limit. So they proved what is the PDE that govern the macroscopic evolution of the density of this function, which describes the density of rod at time t. Then there is a chapter on hard rods in the book of Spohn of 91, where he introduced them as one of probably the simplest yet not trivial integrable model. And then in 97, Boldrighini and Sukhov have a paper on the fluctuation. So after the hydrodynamic, they proved the fluctuation of the homogeneous rods. And then recently, Doyon, Yoshimura and Co. in 2017, they have this paper on a very similar model, which is called soliton gas, which generalizes, more complicated, but generalizes the hard rods model. Okay, so now, I have described how hard rods evolve in time. So now let's forget for a moment the world of hard rods, and we go to the world of Frigas dynamics. So the world of Frigas dynamics is very simple. Mathematically, a particle of gas is defined again as a three-dimensional point. X is X, V, and R velocity. So V is the velocity, X is the position, and R is just a mark now, a mark and a real number, for which the evolution. So the evolution does not depend on the mark of the particle of gas. And the evolution is just, so in this particle, they travel ballistically, ignoring each other. So the time evolution is described by this operator, capital T, little t. Okay, so this is the Frigas evolution. And of course, you see, we introduce this mark R just so that we can have, so the point is to have a sort of connection, one-to-one bijection between the world of the Frigas and the world of the hard rods. Okay, now some quantity that are useful regarding the configuration regarding Frigas configuration, capital X. So we define the mass of the configuration by the sum of all the marks of the configuration, and the sign mass as the sum of all the marks taken with positive number if the mass between A and B for A less than B, and with a negative sign if B is less than A. And of course, if A is equal to B, we say that the mass of the configuration for A equal to B equal to 0, A equal to B is 0. Okay, then there is another quantity which rely on the mass of the configuration S. It's called mass or length flow, and is given by the mass of the particles. So it's given by the mass, the sum of the marks, which is the mass associated to those lines who intersect the segment, in the picture is the black segment, with velocity less than v. So they intersect the segment from left to right. So the black segment is described by x plus vs, where s goes from 0 to t, minus the contribution of those lines intersecting the black segment with velocity bigger than v, so crossing the segment from right to left. Okay, this is just a convention. So this is in the picture, the J is given by the positive contribution of the blue and purple marks minus the contribution of the green mark. For the free gas configuration, we will only consider configuration with finite length flow. Okay, so if everything is clear now, I would like to show you how we can go from the free gas to the hard rods. Okay, so to do that, I have to introduce two maps, the dilation and contraction map. They are always defined around a point for the dilation and to a point for the contraction. In general, the point is general, but will be the origin for simplicity. So how do they work? So the dilation map around the point A takes in input a configuration of free gas, and then dilated according to the mark of the free gas particle. Of course, if there is non-zero mass between a particle and the point with respect you are considering the dilation, you have to take this into account. So to be clear, so for example, you see the blue particle is dilated, taking into account also that you had to dilate the green one. Okay. Similarly, if the contraction map takes into account hard rods configuration capital Y, and the output would be a free gas configuration. So you see, so the point, the particle, let's say next to the point A are just shrinked, but then for the blue rods, I have to take into account, this shift that I also have shift. I have to shift with the green mark of the rods, which is between the point and the other rods. For positive marks, these two maps are one the inverse of the other, so we can always go from one word to the other using the D and C. Okay, this was just in picture, but this can be rigorously defined. You see, so this is just in math language what I said. I take the dilation map. I shift the whole configuration. I delete the whole configuration by deleting each particle, the new rod, so the rod corresponding to the free particle X will have position X plus the mass between A and X if X is after and is bigger than A, or with a minus sign. And similarly, the contraction map will be, so the point of the free gas particle associated to the rod in the configuration Y will be its position Y minus the mass of the configuration between the point A and Y, with a minus if Y is bigger than A, or I change sign if A is bigger than 1. Okay. So now using this map, and in particular this map from the hard rods to the free gas, it is possible to define the position of a hard rod in terms of the position of the free gas particle. Okay, so if we consider an ideal particle, XVR, then the position of the rod associated to that particle will be the dilated point X, now with respect to 0, plus the contribution of the bare speed, plus this shift that I have to do that takes into account all the collision. If I have just one rod or one particle, then there is no collision and the J is 0. Then the evolution of the whole configuration will be given by the evolution of each single rod, and we denote it by UT. Okay, so this is in terms of the ideal gas particle. Of course, I can also define the position just forgetting about the Frigas dynamics, but the position of my rod, now I call it U, but it's morally the same because it will be the initial point Y, which is already dilated because I am in the hard rods world, plus the contribution of the velocity, plus this shift that is given by taking into account all those lines intersecting the trajectory of my rod. So you see, I think the picture is very explicative here. So if I have no other rods, the position at time t would just be y plus vt. You can see in the above picture, but y below, you see that actually you have to jump, this sort of jump, which are negative for the orange and purple lines, because they have velocity bigger than v. And it's negative for the contribution of the green and the brown line, because they have velocity smaller than v. And so this produces a shift, which has to be used to adjust the position at time t of the rod. Okay, so these two are completely equivalent. Just one has the interpretation with the free particle, and the other one is the one of the rods that I gave at the very beginning. So using the maps D and C, it is also possible to define the position of the whole configuration all at once. And this position will be, so the idea is the following. I'll take my initial configuration at time 0, capital Y. I have, so I contract it with respect to the origin. Now I have a configuration in the Frigas, for the Frigas world. I let the operator that describe the time evolution evolve, so that's the capital T. Then at time t, I delete my evolved configuration. And now again, I have to adjust, to use this shift to adjust the final configuration at time t, because I know that every time two rods collide, there was a jump of plus minus the length of the rods. And so this is again another way to describe this evolution. So SOT is of the configuration produce a shift of OT, and what is this OT? Again, is the net flow of, so you can think of it as, as the position of a zero length, zero speed rod placed at the origin. So imagine this red point would be really at the origin, and then it's, so the J, which is equal to the J of the segment, of the black segment, that, okay, maybe I can use this, so exactly, so it's the J of this segment. This is the shift I have to incorporate in the final evolution in order to take into account on the shift of the colliding rods. Okay, so this is, I have one last picture just to see that, okay, this is again, okay, if you want a simulation, so the right-hand side, there is just, forgetting about the Frigas dynamics, I just have three rods which evolve with this rule that I gave. So they just, when they collide, they exchange their position and they keep evolving. And then on the left-hand side, I have exactly the same, but taking into account that I want to see the evolution, not in the world of the rods, but in the world of the particles. So I have my rods, my initial configuration of rods Y. I use the contraction function. Then I let the free gas evolution evolve, so they just evolve ballistically. And then I delete the configuration of the free gas at time t. And then I have to account this shift S0t, which is given again by the lines, by the contribution of the lines crossing this segment, this blue segment. Okay. So up to here, everything was, so up to here, let's say, was everything already known in the paper of Boldrighini, Dobrushin and Sukhov. You see already the definition of these maps. What is different now is that they gave several and technical conditions such that you can apply the hydrodynamic result. But for us, it's completely different. So we say that we consider a Poisson process, three-dimensional Poisson process, capital X, which will be the initial configuration of the free gas war. So this is why I stress on the free gas war, because everything we prove for the rods is proved for the free gas, where things are simpler, and then we go back to the rods. So now I am in the free gas. So X is a Poisson process with mean measure mu and intensity F. In particular, the mean measure of a measurable set A is given by this formula. And X epsilon is a rescale Poisson process of intensity epsilon minus 1F. Okay, so this is this is the setting, the initial setting for the hydrodynamics. Now I define this function, capital H, which you see, it gives again another interpretation of all the story. So imagine so the function H works like this. You have a plane, xt plane. You draw a line, for example, the blue one, and you gave high 0 to the half plane containing the origin and high r, the mark of the line, to the plane containing, to the other plane. And then you do this for all your line, and your function H is exactly tells you, okay, tells you which high gives to each plane or semi-plane of the origin. And the contribution of all this H is called chance of Lantejoule field. So now if you look at the two pictures below, you see that the left one is just my free gas evolution, while in the right one I have two interpretations. One, if you see this second picture two-dimensional, is just the evolution of 3 hard rods. But if you see this picture three-dimensional, then this is the chance of Lantejoule surface. You see, it's basically some terrace of high given by the mark of your line.
Chiara, do you have 5 minutes?
Yes. Okay, thanks. Okay, so this is an object of interest because for these rescaled surfaces, it's not easy, it's not hard to find a low large number, which only relies on the low large number for Poisson processes. I was not planning to give any proof, but then what is interesting is the hydrodynamic empirical measure for the hard rod process. So the empirical length measure is defined in the following way. So it's rescaled. Y epsilon is the dilated of with respect to the origin of the rescaled Poisson process epsilon. So the idea of the proof is to prove everything in the X epsilon, and then with the dilation we go to the Y epsilon. In particular, Y epsilon. So in general, in hydrodynamics, you rescale space and time. Here, we don't rescale space and time. It's more natural to just rescale this configuration. So Y epsilon is the configuration of rods of length epsilon r and distance of order epsilon. Then you do some assumption on the time 0. So you have this converger, which in particular regards this G of Y VR. And then you want to prove that at time t, a similar convergence holds, where instead of G, you have a GT. And this GT and G, in particular GT, you want to characterize GT. In order to characterize GT, you say that it's the unique, it's the solution of some PDE, which is called the hydrodynamic equation. For the hard rod system, this is the PDE. The G of the initial limit at time 0 will be the initial condition of the Cauchy problem. And you see there is this effective velocity, which is complicated, but it's the contribution of what? Of the bare speed plus you take into account all the collision. In particular, this effective velocity is the time derivative of the position u of your rod. Again, here you can see there is also a larger number for the rescaled position of the rods, u epsilon. And to prove this, we go through the proof. We rely on the proof the larger number for the chance of Lantejoule field. And last thing that it's worth saying is that So another way to write these effective velocities are complicated. Another way to write is this equation, which is implicit because the effective velocity are also on the right hand side. But you see that so in a sense this is general because it seems that not only a system of our rods have this kind of effective velocity, but there are more complicated systems like the KdV soliton gas, which have formally exactly this equation for the effective velocity with a different collision rule. Because here you see that phi is just plus or minus r, which is the jump, if you remember, the jump of the rods plus or minus, depending if the colliding rod has velocity higher or lower than the one he has. Okay, so I thank you for the attention. Okay, I just wrote some open questions that might be interesting, but thank you.
Thank you very much, Chiara. Okay, so are there questions, comments? Okay, I have one, perhaps two. At the beginning, you had mentioned that the length of the rod may be even negative.
Yes, I mentioned that.
What does it mean?
So I'm not a physicist, so in fact, also to me, it's it's not very intuitive. But I asked physicists, and they say it was interesting. I can tell you that in order to prove the result from a mathematically perspective, it's not so much harder to just say, okay, the length can be a negative number. It's hard to visualize. The models with rod with negative length might be, it should be related to this Lieb-Lineger model, which I don't really know, but it's studied in physics regarding cold atoms. Yeah, but I asked Benjamin Doyon, who is a super expert of generalized hydrodynamics, and he said that for him it makes sense. So
okay.
So it was the motivation. This was the motivation to push because we had everything for R positive, and then it was the motivation to push for a negative R that to physicists made. I don't know. They said it made sense, and so by the mathematics was not so much harder.
Okay. So okay. In other, if there is no one, okay. Another question. I mean, I imagine that because the scattering, the scattering shift after the collision, it just depends on the variable r, which is, it is a label of each particle, of each rod. I imagine that if the scattering shift also depends on the velocities of the particles, the things are much more complicated.
Yes, indeed. Yeah, we haven't thought about that, but it would be nice to have some extension of models where exactly things are more complicated in terms of how they collide, like the collision rule. But also for me, it would be interesting to see more probability in the collision rule, while here everything is deterministic. So this is the reason of my next question here. That would be nice to see some random redistribution of the length maybe after the collision. This is a bit inspired by the Kipnis-Marchioro-Presutti model, which is a stochastic model of redistribution of energy. There the quantity of interest was the energy, but the redistribution is random. While here the only random object is the initial configuration given by the Poisson process. So indeed, yeah, it would be interesting to see more complicated models.
Okay, so if there are no other questions, okay, thank you again very much, Chiara.
Thank you.
Thank you.
So much.
Thank you.